It was easy to classify the critical points in the previous examples because the functions themselves were relatively simple. So if we take a look at this function of a paraboloid, we found that the critical point existed at 0, 0. And if we were to measure the change in a function relative to its critical point, we found that it was always negative for all values of x that weren't at the critical point. As you move away from the critical point, the function always decreases in value, so that means it must have a maximum at that point. When we took a look at the cone, it also had a critical point at 0, 0. When we measured the change in the function away from the critical point, we found that it was always a positive quantity. As we move away from the critical point, the value of f is always increasing, meaning that we have a minimum at that point that we're interested in. Unfortunately, other functions in general aren't this straightforward to analyze. So what we need is a procedure by which we can classify critical points. This procedure is going to be based on Taylor expansions of a function. The Taylor expansion at a point would be approximately the value of the function at a, its first derivative at a times x minus a, and then its second derivative at a divided by 2 times x minus a squared. If we cut off the expansion at this point, this is a quadratic approximation of the function. This requires that we have a function that's defined at the point, a derivative that's defined at the point, and a second derivative that's defined at the point. But we're also going to assume that they are continuous at the point because we want the resulting approximation to be continuous as well. So we are going to assume that the function f has continuous first and second derivatives at the point x equals a. If we have a critical point at x equals a, the only option is that the derivative must be 0. We don't want to talk about the situation where the function doesn't have a derivative at a, because then we wouldn't be able to get the second derivative out. The Taylor expansion of the function is approximately f of a plus 1/2 second derivative at a times x minus a squared. Now near x equals a, the point we're going to study is a plus h, where h is just some small number. If I were to plug this in as my location in the Taylor series, I'd have f of a plus or minus 1/2 f double prime of a plus h, subtract a is just going to cancel out there. At a nearby point, we could say that the difference in these two functions is approximately 1/2 times the second derivative at that point times h squared. This quantity right here represents the difference in the function as I move away from that critical point, x equals a. Near a critical point, if my second derivative is a positive number, if I were to study my function, it looks nearly like a parabola. There's the location a. I have an upward parabola here. And that means that this critical point here is a minimum. Remember that when we have a second derivative, we're talking about concavity. So this would be concave up. If I have a second derivative value that's negative, it would be concave down, and it looks like a downward parabola. My function looks roughly quadratic, but because its second derivative is negative, it's a downward opening parabola, and that tells me that this critical point is a maximum. The change in value here would be a positive quantity away from a, and here the change in the value would be a negative quantity as I go away from a. This process right here is called the second derivative test for classifying critical points. So what we are going to do is generalize this second derivative test to a function of two variables. Now, it's possible to generalize this to functions of more than two variables, but at that point it requires complete commitment to linear algebra, and we are just going to get the ideas across here in this special situation. Now, just like before, this is going to be based on a Taylor approximation of my function at some critical point. So we'll say that this point AB is the critical point of my function. Now, when you have a Taylor approximation of a function, what you're saying is the following. approximate the function with a surface. We've already seen a linear approximation put a tangent plane right at that point. Earlier, we found that the linear approximation of this function would be represented by f at the critical point AB, plus we had these first partial derivatives, x partial derivative at the point times x minus a, plus the y partial derivative at the point times y minus b. Instead of having a linear approximation at the point, what we're going to try to do is have a quadratic approximation. So fit in a quadratic surface at this point. So a quadratic approximation means that we are going to find the best fitting quadric surface at the point AB. So we are going to try to find some sort of quadratic of this form. Ax squared plus bxy plus cy squared plus dx plus ey plus f at the point AB. Just like you learn about in single variable calculus, if you differentiate this quantity and you equate it to the original function and its partial derivatives, what you will find is that the quadratic approximation of your function near this point is going to be f at AB. You're still going to have those same partial derivatives that you talked about first. These are the linear terms. But what ends up happening is now you get a host of quadratic terms, and they're going to be related to the second partial derivative. So what we'll have is the second partial derivative with respect to x minus a squared, f of xy ab times an x minus a and a y minus b. There is no 2 in the denominator. If we wanted to, we could think of it as 2 over 2. Second partial derivative with respect to y in a y minus b squared. So this is the quadratic approximation of the function at the critical point AB. Or you could think of it as the Taylor approximation. Now you can see from this formula here, we require that the function, its first order partial derivatives and its second partial derivatives all exist at the point AB, but we're going to go one step further. In order for the resulting function's approximation to be continuous, we are going to say that all of these functions are continuous at the critical point AB. Now we're going to consider some sort of critical point, AB. If we have a critical point, it's only going to be possible for us to talk about the ones where the first partial derivatives are equal to 0. We can't consider the situation where they don't exist, because then we wouldn't be able to have the second partial derivatives. All of these terms are going to be 0. And then the Taylor approximation is just going to be left with the function and these quadratic terms. F of a and b plus the second partial with respect to x over 2 x minus a squared plus 2 of this f of xy, this mixed partial derivative over 2 x minus a y minus b plus the second partial derivative with respect to y over 2 y minus b squared. We want to study the change in the height of the function as we move away from the critical point. We're going to let x be a point that's nearby the critical point, the x value of the critical point, and we're going to let y be something that's near the y value of the critical point. So h and k are just some small displacement away from it. What this is going to tell me is that delta f is going to be the value of my function at a plus h, b plus k. I'm going to subtract the value at the critical point. I'll get the second partial derivative with respect to x at the critical point over 2 h squared plus 2 of this mixed partial at the point divided by 2 times hk plus the second partial with respect to y times k squared all over 2. This expression right here, we could factor out a 1/2, and what we would have would be this second partial h squared, 2 of this mixed partial hk, and then this y partial times k squared. This is what's known as a quadratic form. The sign of delta f depends on the sign of this expression. So if we can study this quadratic form and understand how it behaves, we will be able to classify the critical point. We will call this some p of x and y. Now we're going to talk about this in a general form, alpha h squared 2 beta hk gamma k squared. To understand the sign, what we have to do is rewrite this by completing the square. The first assumption that we have to make is that this alpha isn't 0, or in our case, that the second partial derivative isn't 0. If that alpha is 0, then we could just move to this gamma term in front of the k squared. And if that term's also 0, then there's another analysis to make just by using that middle term. I'm going to remove an alpha from everything here. So we'll have this polynomial. We'll have an h squared plus 2 beta alpha k times h. And then we'll have gamma over alpha k squared. So this middle term, 2 beta alpha k, I need half of it, so that means beta over alpha k, and that means I need to square that middle term. This is the term that I need to add in to turn the first contribution into a perfect square, but remember, I'm not allowed to add something in for free. I have to take it out as well to keep the value equivalent. This quadratic form can be written like this. I'll have an alpha h squared plus 2 beta over alpha k times h, beta over alpha k all squared. I'll have gamma over alpha k squared subtract beta over alpha k all squared. These first three terms turn into a perfect square, h plus whatever this term is here, and the whole thing gets squared. The second expression here, I will have a gamma over alpha subtract beta squared over alpha squared times k squared. And I'm going to do one more rewrite. I'll have alpha h plus beta over alpha k squared, k over alpha all squared. I'll have alpha gamma minus beta squared. This is a completely positive term. At the very least, it will be equal to 0, and that will only happen when I'm at the critical point. This expression right here will also be positive. It can only be 0 right when I'm at the critical point. So I'm going to call this expression right here D. A quadratic form is definite if it has the same sign for all of these points h and k. That's what we're really after. I want to be able to determine whether this quadratic form is always of the same sign. We are going to say that it's positive definite if it's always positive, and we're going to say that it's negative definite if it's always negative. So our primary goal here is to determine whether or not it's positive definite or negative definite. This will help us understand how our function is going to change as we move away from the critical point. So what I'm going to do is take this quadratic form and now rewrite it in terms of the original contribution. So we have the following. This was the second partial derivative at my critical point. This is fxy over fxx. K was some small distance away from the critical point in the y direction. This was k over fxx squared, and this will give me fxx fyy subtract fxy squared. This change in the function value is approximated by this quadratic form. This term is always positive. This term is always positive. This term we're going to call D. If this quantity D, fxx fyy minus fxy squared, is always positive, then the quadratic form delta f is definite because every single term in the square bracket will always have the same sign. If this term fxx is greater than 0, and D is greater than 0, then this quadratic form will be positive definite. The expression in the front here determines the sign overall. That means delta F will always be greater than 0 away from the critical point. If you have a picture something like this, at my critical point, no matter which way I move, the height of the function is going to increase. That tells me that I'm going to have a minimum. If my second derivative is negative and I have a positive D, then I will have a negative definite expression. Everything in the bracket will be positive, but that second derivative term out front will be negative. The change in the value of the function as I move away from the critical point will always be negative. Regardless of where I am on this surface, as I move away, the height must decrease. So I'm going to have a maximum at that point. Now, what's really important to note here is that these expressions are true for all values of h and k. It doesn't matter which direction I go in. The sign will always be the same, and that's what makes it definite. We are sure of what is going to occur. There are other situations where things will happen that we are not so clear about. If this quantity d is negative, then the term in the bracket could change sign for various h and k. Now, if this term d here is a negative term, it's possible that we could get zeros underneath, we could get negative expressions inside, we could get positive expressions inside. This delta f could sometimes be positive or it could sometimes be negative, depending on the direction that I move away from the critical point. So for example, this hyperbolic paraboloid, we will have a critical point, and if we were to move along this direction, the function would increase, my delta f would be positive, but if we were to move in a different direction, something like this, we would have a decrease, the delta f would be negative. We cannot say with certainty it's going to behave the same way for all points h and k. The critical point you have is a saddle point, and the quadratic form is called indefinite. The last situation that we're going to talk about is if d is equal to 0, then the change in my function, which is approximated by my quadratic form, is going to be the second partial derivative like so, h plus fxy, fxx, k all squared. Now, once again, the sign of this depends on the sign of this term. It could be positive, it could be negative. Even worse, if h is equal to negative fxy over fxx times k, then this change in the function could be 0. So unfortunately, this situation tells us no useful information. We have to study it individually on a case-by-case basis, and it won't tell us anything with certainty for every single situation. Now, I know that this is quite a mouthful, so we're going to try to summarize this. This is what's called the second derivative test for a function of two variables. This second derivative procedure is extremely useful for finding and classifying critical points as relative maxima or minima or saddles. Let f have continuous first and second partial derivatives near some point AB. We are going to let AB be a critical point of the function, which then implies that the first partial derivatives at that point are equal to 0. And then we're going to let this quantity d be given by this product of second partial derivatives. Now, there's a very convenient way for you to remember this. This is simply the determinant of this matrix of partial derivatives. This matrix is called the Hessian matrix, named after a mathematician called Hess. We are simply taking the determinant of this. If this second derivative at the point is positive and this quantity d is positive, then what happens is I have a relative minimum at my point AB. If this second derivative is negative and this quantity is positive, that tells me my point AB is a relative maximum. If this quantity d is negative, AB is a saddle point. If this quantity d is 0, then I will have no information from this analysis. I can't figure out what it is that needs to happen with my function. I have to study it in some other way. So let's take a look finally at an example of this. So let's find and classify the critical points of this function. F of x and y is equal to 4xy minus x to the 4 minus y to the 4. What we're going to need to do is find its partial derivative. So the x partial derivative of this expression, I simply need to take this partial derivative right here. And what this ends up giving me is 4y minus 4x cubed. The y partial derivative here is a similar idea. I'm going to get 4x minus 4y cubed. The critical points happen when the gradient vector is equal to 0 or the gradient vector doesn't exist. In my case, it must exist. So what ends up happening is that I now have a system to solve. I'll have y minus x cubed is 0 and x minus y cubed is 0. We'll call this equation 1 and equation 2. From equation 1, I know that y is x cubed. If I put that into equation 2, what I'll get is x minus x cubed cubed is 0. X minus x to the 9 is 0. And this tells me that x into 1 minus x to the 8 has to be 0. This has solutions that either x is 0 or x to the 8 is equal to 1. If you were to take the 8th root of everything on both sides, absolute value of x is equal to 1. So x is 1 or negative 1. Now, to find out the corresponding y values, we sub everything back into here. When x is equal to 0, clearly y is going to be 0, so 0, 0 is a critical point. When x is equal to 1, we'll have y is 1 cubed, which is also 1, so we'll have 1, 1 as a critical point. And x equals negative 1 tells me that y is negative 1 cubed, so negative 1 is a critical point. So what we then need to do is determine the second partial derivatives. So the second partial derivative of this expression, the x partial derivative of 4y minus 4x cubed. So this is going to give me negative 12x squared. The mixed partial derivative, remember, because this function has continuous second partial derivatives, I can take this mixed derivative in any order I want. And what ends up happening is I will just get a 4. You can verify for yourself that it always works out the same. And finally, if I were to take this partial derivative here, I'll get a negative 12y squared. The quantity d is what I need to measure. fxx, fyy minus fxy squared. This is going to give me 144x squared y squared minus 16. So it's easiest to analyze the critical points using this little table. At the point 0, 0, the second partial derivative with respect to x is 0. The value of d is a negative. When d is negative, that means I have a saddle point. At the point 1, 1, this will give me a negative 12. This d value will be positive. So if I have a negative second derivative and a positive d value, this tells me that I have a relative maximum at the point. And similarly, I will have a negative 12 and once again a 128. So I will have a relative maximum.